Imagine a caveman roaming the streets of New York, bare-chested, breathing in the air of a nearby pizza shop, surrounded by vehicles and flashing cameras, staring back at the people going haywire at the next great Comic-Con cosplay, the caveman himself. And although our little caveman will have a lot to be surprised at, what do you reckon he'll notice first? Well, that he's become lost on his way back to his cave, of course. But what will he notice second? Probably the tall buildings that to him must look like the product of some convoluted witchcraft. An object us modern-day wizards call skyscrapers. Skyscrapers have come a long way since the first one was opened in 1885. That skyscraper was 45 meters tall, and today it wouldn't even qualify as a skyscraper. Now, there is no universally accepted definition, but modern sources define skyscrapers as being at least 100 meters tall. Isn't it surprising how none of these seemingly stick-shaped towers fall? Yet your short Jenga tower can't seem to withstand one pull of a block? Well, tell your short Jenga tower to get these tests done. Disclaimer though, in most cases, there is no universal list of tests that every skyscraper has to pass. There are some common tests for most skyscrapers, but the rest are influenced by conditions specific to the location of the skyscraper. You can't not test a skyscraper in Japan for seismic fluctuations, for example, because it's satisfying when the Jenga tower falls. But the Japanese, from 40 stories? Yeah. Gone are the good old days when all I had to do was test a skyscraper for structural stability, load-bearing capacity, material, fire safety, foundation, wind load, architectural design and approval, and have it good to go. No, it's much more complicated now. For the purpose of this video, let's divide the tests into two classes: universal tests and conditional tests. Universal tests being tests that most skyscrapers have to go through, and conditional tests being those that are specific to location and design. Most skyscrapers have to go through a structural analysis through computational models to simulate the building structure under various loads and environmental factors. Pretty sick how you don't have to hit the damn building with a wrecking ball to see if it'll stand. And what else is on the most wanted list for skyscrapers? Wind. Skyscrapers hate winds. Sometimes they even run away from them because they hate them so much. Except they trip and fall, and you don't want a 200,000-ton behemoth accidentally tripping in the middle of a city. How do you test for wind then? Well, first of all, low wind areas don't really need to get this tested. But buildings with weird shapes definitely do, as they are more vulnerable to the wind due to their awkward load distribution, wind flow disturbances, and vortex shedding. Vortex shedding is when low-pressure pockets build on either side of the building, causing it to sway. To test for wind, models are created of the actual building to scale. Then these small models are put in a wind tunnel, and they are attacked by winds from different directions and speeds. The test is simple, but the engineering that goes into passing it isn't. Wind tunnels are powerful, and the models of the buildings themselves are interesting. One more thing skyscrapers can't seem to digest are earthquakes. Seismic testing is done through shake table tests to simulate earthquake conditions on a model. Rarely you find a full-scale section of the building being tested. And to ensure that all these tests for the part of the building that is above land are actually useful, a good foundation is necessary. And guess what? We have a test for that too. This one is interesting, as it has little to do with the building and a lot to do with the land. Soil samples are analyzed to determine how much load they will be able to bear. Load tests are another part of foundation tests that involve applying weight to piles or other foundation elements to ensure they can support the structure. And to ensure that the structure doesn't burn to the ground after all this effort, there are fire safety tests. Now, you don't really try to burn the building down. As we know, we're too modern for that. Instead, individual materials and structural elements are exposed to high temperatures to check whether they can resist ignition or not. Just in case a building lights up on fire anyway, fire safety systems are also put in place. Evacuation drills and simulations test these systems for their effectiveness. Samples of steel, concrete, glass, and other materials undergo tests for tensile strength, compressive strength, impact resistance, and durability. This is also called material testing. Elevator and mechanical systems are tested for speed, reliability, and emergency effectiveness. Facade and cladding tests are organized to ensure that the outer covering of the skyscrapers can withstand the elements, and more. Cladding is the covering or coating on a material, and a facade is the front part or exterior of a building. These are kind of similar to the ignition tests, except the materials are put under different types of stresses. This includes wind pressure, thermal stresses, structural load, seismic stresses, water penetration, air infiltration, impact stresses, vibration stresses, chemical stresses, acoustic stresses, UV and weathering, cyclical stresses, and all kinds of different applications of load. And after this elaborate yet still incompletely discussed affair, the building awaits certification. Final certification is granted after all inspections and tests. This ensures that the building is compliant with all safety and regulatory requirements. Interestingly, most tests also keep in mind the impact the structure will have on its surroundings once it's built. In that sense, they don't just test the building's reliability itself, but also if it will jeopardize structures around it. Take the wind test, for example. Not only does the tower have to withstand the wind itself, the builders also have to ensure that it doesn't alter the wind patterns in the surrounding area. This goes back to the basic theme that the developers have in mind: to make sure the building looks good and to make being inside it pleasurable, because altered wind patterns and a difference in the amount of sunlight that reaches the city floor, for example, affect how long people are likely to spend in that area. And let's be honest, a bad environment surrounding the building, because of the building itself, will come back to bite the developers later. Going off on the same tangent, building skyscrapers can be difficult due to factors other than complexity and cost. For example, in European cities like Paris, the difference between the appearance of old architecture and modern skyscrapers can make it hard to get approval from local authorities to construct new skyscrapers. There are also some common sense measures, like prohibiting structures above a certain height in extremely volatile areas. You generally don't want to build a skyscraper in zones of high seismic activity or the middle of Antarctica. Good structural planning and integrity is important everywhere, but it's assigned even more weight in projects such as skyscrapers. Even a minuscule error in judgment or an apparently insignificant oversight can put the lives of several people at stake. So it's kind of comforting that there exist so many tests and so many methods of offsetting potential disasters. These obscure fields of engineering and technology are the ones that often reveal the true extent of technological welfare that has been propagated through development, and makes one really appreciate experiencing the value of this new era in its making. Nowadays, design flaws in such projects are not unheard of, but they rarely put the integrity of the entire operation at risk. Modern development and technological advancement have ensured that potential mistakes are easier to spot and fix. Skyscrapers need to battle major forces of nature, such as gravity, heavy winds, and seismic fluctuations. And it's inspiring that we have so many domains of study, each catering to something so specific, yet so important. It's like a giant cogwheel that's operated by smaller cogs, and the absence of even one could cost the entire model its movement.